last lecture we ended with a fictitious sophomore physics Earth, a picture there, that we're going to use today to develop the orbital mechanics for mainly the inside of the sophomore physics Earth. And in the process of doing that, we'll be developing some geometry of elliptical orbits. The first thing to prove, of course, is that it is an elliptical orbit. Now, the two symmetry fields, the two fields that are the most famous for physics, and also the ones we can do analytically, the harmonic oscillator, but in particular the isotropic harmonic oscillator, IHO. It's written at the top of that screen right there, is the highest symmetry. It has a symmetry unitary 3, which doesn't mean much to you right now if you haven't studied group theory, but we'll be coming at that later on in the course. But for this review section, I want to do the most elementary derivations of various things that happen to those orbits, and point out some interesting size as well. But while we're doing that, while we get the geometry of the solutions to this one, and in passing, I'm going to, and as I says, they're derived in Unit 5. We won't deal with the intricacies of the Coulomb potential, which has the sort of opposing symmetry on the orthogonal group in 4 dimensions. Makes it possible to solve that one analytically, and also do geometry with it exactly. So we're mainly going to just derive the things that have to do with the sophomore physics Earth, the isotropic harmonic oscillator. Now the ellipse geometry that does all of that also lets us introduce the geometry of quadratic forms. And we've already dealt with the quadratic form in the very first lecture, but this one is more general and has to do with, connects very nicely with this. The things that are here are very sort of sneaky derivations, but they're quite clear. This is a little more wonky, this stuff down here. I apologize for doing the wonky stuff second when you're already exhausted from maybe doing this first part. But in any way, that is the best way I found to set this particular lecture up. And so let's just go ahead with it. Now, as usual, there are some links here to some things that we'll do later. They're more distantly connected with what we're doing here. But in any case, the basic idea of this particular isotropic harmonic oscillator that we get, if we have a uniform gravitational body or a uniform electrostatic collection of uniform density charge. The idea of this is the one-dimensional force law, and we've scaled everything to geometrical units, so this is a really neat thing to remember about an orbit in an isotropic field, is that if you scale it using geometrical scales, then the force vector is just minus the r vector, the position vector. So wherever you are in this thing, the force that you're feeling, very small as you approach the center, getting larger as you move away linearly, is just a vector pointing opposite to the position vector that locates it. And therefore, the 2 or 3 dimensional equation written in vector notation is as stated here. And then the idea is that if you let that thing go, it would just oscillate back and forth between that and that. If you had a mass here that could move freely, and here I'm indicating a little tunnel through the thing, so this is making it a little bit more realistic so that somebody might be able to actually ride in a tunnel if the Earth weren't so damn hot in the center there. You would again have something that would oscillate back and forth in unison with this thing. So the two would follow each other, presumably just a little, either collide or pass, and then continue out the other side. So when we work out the frequency of the oscillation that occurs inside there, that is independent of wherever you start or whatever amplitude you use. And that's a characteristic of a harmonic oscillator. In this case, an isotropic one, where each dimension x, y, or z has this total energy. It has this Lagrangian. This is a Lagrangian with a potential. And the mv squared and the kx squared, the fact that you can write the thing as the sum of squares, that's what leads to a really nice derivation of the equation of motion without using very little calculus, and no differential equation is mentioned in this particular derivation. And I'm going to do the same thing with a couple of things during this lecture. So this is where we begin. In fact, we're almost done with the derivation once we've done this. This is another example of that scale a circle out of an elliptical structure. We had an ellipse that defined our superball collisions, and then we scaled that with the square root of mass to get a circle, which we call the Strongian. And then if you scale it with the whole mass, then you get the Hamiltonian. So that geometry of ellipse, circle, and then ellipse that's conjugate to the original ellipse is part of all of the stuff we'll be discussing in the next few lectures. Okay, so having done that, that is, having written this thing as this thing squared plus this thing squared, we immediately assign a sine and a cosine to that. And that's kind of it. Once we've done that, we have derived what we need, all we need to know about the orbits of this imaginary neutron star that's cutting through the Earth, or else just some device that somebody builds, say a great big iron sphere out in space, and they let a little mass drop, and it slowly moves through the center here, so it comes to that point right there, and continues if there's no friction forever. Now let's go ahead and finish this derivation. The basic idea here is to find an angular velocity, that is a time derivative of this whatever angle, and there's some kind of angle here, a phase angle, which is really the important part of this lecture, is finding good ways to use geometry to find phase, and do it in a way which is going to be directly applicable to the connection between classical and quantum mechanics, which we'll be getting to later lectures. So anyway, just using this first step here, that is the velocity that we're talking to, solving this thing equal to that thing, and getting the velocity as just a cosine times a square root of energy over mass is the first step to doing this, and at the same time taking the velocity as a derivative and doing a simple calculus trick so that we can get a derivative with respect to that phase angle, whatever that is, and we need to define that geometrically in just a little bit here. But that then leads us, just from our definition of that angular velocity in terms of the phase angle, whatever that is, that's the thing we'll really be measuring here, or working with for oscillator equations, which is what we're after here. Okay, so that's the first part of the thing that involves just the ratio of the energy to the constant that defines the potential, the spring constant, if you will, of the mass inside the Earth, and the gravity of providing this oscillator. And then next after that, to get that lined up here, the next thing is just take the angular velocity and divide 1 by 2, basically. Okay, so this yields what we're after, the frequency of the Earth. What happens? What frequency does the Earth ring at? That's really what we're getting here. But we can make it. We can make this, I think, more to our imagination. If you imagine, won't go that far. If you imagine that you could make a really straight track, say a magnetic levitation track, and just set it up here, both, say, using a laser beam. A laser beam, except for the fact that general relativity eventually curves the laser beam a little bit, that's ignorable here. Using a laser to machine a absolutely, almost absolutely straight and level. You'd have to get the thing so it's perfectly level, okay? So that if you put the thing that's going to ride on it in the center, it sits there. And then when you pull it to the end of that thing and let it go, what's it going to do? Oscillate, just like all of the masses in this thing. So let's imagine a tunnel being made, tiny little pixel up at the top there, right? It's going to have the same frequency as this one. So in 84 minutes, it's going to go 42 there, 84 back. That's kind of neat to think about. In other words, you can measure what an orbital frequency is if you can make something really precise with no friction, magnetic levitation, laser machine, right, so that it rides on that track. And back and forth it goes. Okay. You can make it longer if you can afford it, right? It's still going to pretty much do the same thing. Until you've really made it long so you've got things sticking out over the Earth, then you're doing something else, right? You're getting another frequency. Okay? A lower frequency, right? Well, that's a good mechanics problem to throw at people. What happens if you make a really perfect, frictionless track and let something go on it? Okay. All right. Okay, so that number, very important, and we're going to work with that to build basically what we call clock dynamics. Now what I'm going to do next here is I want to show you this phasor business, this angle theta, theta equal omega t. This is a device, a geometrical device, that is really useful for studying a two-level quantum system. So, as I've said, we try to make the connections whenever we can here in this course between the classical stuff, which is what is being shown here in these pictures right here. But this, go ahead and put it up there as well. This is the graphical way to calculate an orbit in the sophomore physics Earth, or the orbit that occurs in, well, there are all kinds of things that connect to this, but this is really looking at the structure of the group U2 symmetry that you have for a two-dimensional object, or a two-degree of freedom, two-level system. And just to give you an idea of how that works, there are, let's see if I've got this, the simulation connection is down here. Just to get this thing moving, I think I can Hope for it to come up here, yeah. Okay, so these are two clocks running at that frequency, omega. This is a plot here of the y position versus the velocity y. Now that's an action diagram or plot here with coordinates versus velocity. It's part of it's another way to say phase. This is a certain phase of the oscillator that goes along the x coordinate, and this is the oscillator for the y coordinate. And here's x and y of the orbit that is occurring due to the uniform motion. And all that's different here is that the phase of one of them is 15 degrees behind the other. So this has a delta alpha, called alpha, the initial phase. That is what's giving the orbit in the time. This is the time. Both of these are the time. One of them is just set 15 degrees behind the other. So depending on how you set a clock like that, depending on how the phase is set, and go ahead and run this one so you see it on this side here. See if we bring it back here. This is a really neat tool for a lot of things. If you're doing any sort of polarization analysis, you're dealing with elliptical polarization, this is a graph that tells it all. And this idea of plotting position versus velocity, or position versus momentum, is actually what they call phase space. But position versus the velocity divided by the angular frequency, you'll see why that has to make a circle. But the basic idea of all of our quantum mechanics is what's behind the scene are a bunch of clocks, and they're all left-handed. They're all liberals. They're all going in this direction. You see that has to be, if I'm going to call this the position as a positive, and this the velocity as positive up, then when I'm at the top of this thing, I've got to have a positive velocity. That means I've got to go that way, right? So all of the phasors that lie behind quantum mechanics have a left turn. They go clockwise. Now, engineers, when they're dealing phases for electrical machinery, they're almost always using right-handed. And if you look at all of your exponentials for time behavior in quantum mechanics, they're all e to the minus I omega t. Minus is left-handed. And we'll be doing Unit 2 very shortly, because we do a whole bunch of things with complex variables. But this is really an important one right here. This is the imaginary axis for a phasor. Imaginary is just the velocity divided by frequency. Okay, that's kind of what we're going to be dealing with here. Does that make sense? Now, depending on how you phase these two, you can make a right-handed orbit, or this particular one right here is just exactly that. This orbit here has a right-handedness to it. And this ellipse up here, plotting the velocity, you notice it's plotting x up and y this way. If I take that and rotate it so Vx is horizontal and Vy is, I get the same ellipse as that one in this particular case where the two faces are the same size. Okay. So that's a really nice, not terribly simple, but it includes all of the information about a two-dimensional oscillator. Now with this particular thing, it's a three-dimensional oscillator. So what is missing here? Well, all of the orbits that you can possibly make inside that sphere are going to be ellipses in a plane that is two-dimensional. And it's isotropic, so no matter where I put that plane, I'm doing the same physics. So all we need is this two-dimensional plot to deal with this thing, which is the isotropic harmonic oscillator. Later on, we're going to talk about changing the spring constants for one or two of those dimensions. That will really occur in earnest in Unit 4. But for now, the isotropy allows us just to deal with the plane geometry of ellipses and Phasor circles. Okay, then. Now, I think this is one that you can play with, change, just by clicking on a thing you can change the starting point to anything you want. You make it a smaller clock, and when you do that you get whatever you get. And you can see basically this one right here is Vx versus x, and the Vx is just simply translated over to the Vx that's there. This one has Vy pointing this way, so it translates up to this one. And then x and y here each translate this one here, the y translating to that y, this x translating to that. So there's another ellipse. This is the spatial ellipse. This is the velocity ellipse. Again, I turn this thing by 90 degrees. It lies on top of that one. Okay. Now that particular feature, we're going to use another kind of geometry to show that. But just to get you used to, this is the most general construction for using phasors for a two-mass oscillating system or a two-degree of freedom or two-level quantum system. And that's something we're really going to emphasize in Unit 4. But you might as well see it now because it's very simple. Okay, I'm going to back out of this one. Actually, I not have to back out of that one, it's already going, but I do have to back out of this one. So let me do that. And there's a very finely graphed thing that you can make just as easily. There's the thing that we were just looking at. Okay, and here's a more colorful one. So they're the whole family of ellipses, each differing from each other by a decrement angle, difference angle of 15 degrees. And so you can label a polarization ellipse by where it touches the envelope boundaries. And this one happens to touch at 15 degrees, so that means it's got that plus or minus that difference. Okay. Now, this is another way to do the geometry. We call it the eccentric anomaly. This is more classical. This is more like what Kepler would have done if he had to solve an ellipse problem with a harmonic oscillator instead of what we have. See if I got that on the right thing. Let me go ahead and not use up CPU for that computer. I will pause this one here. Take this one back to let your go forward. So this is the thing that we do next. Is a geometry just straight away. I'm going to take a typical orbit. That is the orbit that I would get if I started at this point as my high point, and then had some basically an ellipse that has a major radius of a minor radius of B. How do you construct such a thing? Okay, very quickly. So this is a quick and dirty way to get the same orbit that we got before, using graph paper that's got a horizontal and vertical to it, setup to it. What this is more difficult to do this method is if you need to do the ellipse that's tipped over like the ones we were just looking at. But in any case, the basic idea is that it's really just another example of what we did last time. It's a zigzag construction. Basically, you do a zig and a zag on graph paper. That is, you pick a point right here on the A part, and you just zig down until you're opposite the point where that line crosses the smaller radius, and zag back to that. You make a little sort of like a high-heeled shoe, a little triangle with altitude and a sole right there. That's what you're doing here, and this is just spelling it out. The concentric circles that determine the A and the B, that's given. And then you just draw a radius at some angle, which is the time, as it turns out. This is very similar to construction we've looked at before, just to construct ellipses without any physical interpretation of orbiting. But here the orbiting is a serious thing. So what we're doing is we're finding, for a particular time, where a particle would have been starting at time equals 0, be on this orbit that is falling along that curve, and there's where it would be at this particular time, t. So the y is just the b cosine of that angle, and I'm sorry, sine of that angle right there, and the x part of the thing is the cosine. Here we're measuring this distance a using the same angle, but it's the cosine that's being written down. So x a cosine, y b sine, that's all there is to this construction. But what's neat about it is, and let's go ahead on both of these to a picture that shows number of the solutions all in sequence there. The get the clicker here to make this one go ahead as well. You can see basically what it looks like if I just put my hand on this thing, and as I go along here, as time advances uniformly, the angle for this, and you can see that here it's moving fairly slowly along that curve, but it picks up speed. Each of these equal time variables, not much happens in the first one, but then a little bit more and a little bit more, and now it's really going at its maximum speed right there. So we're looking at what we're going to discuss in a bit here, the Kepler's law for equal area, equal time will show out of this geometry. So basically, starting from the apogee, think of apogee, the high point of the orbit, actually called the aphelion, it falls to the perihelion. There's the perigee right there. And then it continues falling. Now it's slowing down. Here it's falling to its lowest point in the orbit, closest to the Earth's center, and then it slows down as it reaches back again to a high point on the other side of the orbit. So that's something that you saw happening in the previous construction, that the high point was where it was slow, and then as it passed the center very closely, it was really going quite fast. So that's all being done by this geometry, and there it is. Okay, now the calculus that goes with this. That's the next step here, which is the, there's so many different sides to this story, but they're all quite important for different reasons. There's no Swiss Army knife for physics. You try one technique, you get another tool to further your discussion of the same thing. And you learn a little bit more each time you do that. That's the philosophy of doing all of these weird ways of looking at this. To start off here with just the analytic geometry, the algebra that goes with the analytic geometry, a radius vector for a position. I'm sitting here at a particular position. That's the position vector for this particular moment. Whatever time gives me this, whatever, and I'm using the letter, Greek letter phi for that time frame angle. I mentioned this was the mean anomaly. If a Kepler had done this, that's probably the name he would have given it. And then the eccentric anomaly is the actual position. So the A cosine phi and the B sine phi are built into that particular coordinate there, the zigzag for the actual position. And the next thing to look at is the velocity, the first derivative. Now, calculus tells you that very quickly. Derivative of cosine is plus sine, derivative of sine is minus, derivative of cosine is minus sine. So, and I also pick up an extra frequency factor here. We're being geometrical here, so we're going to imagine when we draw these pictures that omega is equal to 1. So then I don't have to put the omega outside of this particular one. So what I get here is a sine of omega t, and it's a minus sine of omega t, so that's the cosine with the phase shifted upward. Same thing for this one. Both of them have the phase shifted up by exactly pi over 2. So the mean anomaly, the phi angle, has been rotated by pi over 2 in order to get me the velocity. Okay, the velocity was the thing that was being made in the velocity plot in our first look at the Phasor diagrams. But this is a completely different way to think about these two. So here's this thing, and we're taking omega equal to 1, so this has, this position right here is just what's going to happen to this thing a quarter cycle later. Okay? And then we go one more step. The change in position is velocity, the change in velocity is acceleration. So the this is where the force, the Newton 2 will show up here, F equal ma. This is the force divided by the mass is actually what we're writing here for the acceleration vector. Again, all of this is with omega equal to 1 radian per second. So at this point, of course, the second derivative picks up an extra factor of omega squared, which would be on this thing if omega were some other value. Okay. Now the next step, there's one more step here, and then we're done for the harmonic oscillator, and that's acceleration. Let's see. Oh, I'm sorry. We have it's a change of acceleration that NASA gave us a name for that. It's in the Handbook of Astronomics. The jerk, J, okay? Now it's omega third power, but we're just making a vector here that's minus the velocity. This particular guy right here is just minus. But the way to think of it is the phase angle now is at 3 pi over 2. This one is at exactly pi. That was the first one. The first stop here was at pi over 2. Okay? So, we're done, but we need to put one more in here, and this is a bad joke. The change of jerk, I call it inauguration for lack of any other political naming. Okay? We've just had, I think, a really bad case of that in the recent inauguration. But now we have the fourth power of omega if omega were not just equal to 1, which we're taking here. So this one is a full 2 pi, and it's start over again. Okay, so the fourth derivative is just equal to the original position if omega is equal to 1. Okay, so that's the story for this, and I haven't been following very well on this screen or on this one, but let me get all of that so it's in position to be read clearly. All right, any questions about that? Now, in this class, we'll always, whenever we have vector derivatives of time, use a dot. If it's a spatial derivative, we will use prime. That's shorthand. It makes for less writing. I recommend that notation. Okay, anything you can think of that doesn't make sense here? This is fairly trying to make it as clear as possible. Okay, so this is kind of an interesting one to go ahead and look at it on a computer linkage, and that is, I'll go ahead and do that right by just clicking on this one. Actually, maybe I should try to do it on the center screen here. It's bigger. I'll go ahead and put this guy up here. Now this one doesn't move with time. You have to move it. I'm going to run the time here, and that is what you see. It's kind of a beautiful changing of the various vectors that are in that motion there. This, let's see if I've got that. I think that's right. Now this is something else. I'm realizing this is something we haven't really talked about yet. I apologize for that. Let me back out of that. The thing that I really need is, let's see if this one is yeah, this is better. This one, whoops, that's the other thing I want to show, but it's, see if I can see if something weird's going on here.
Yeah, you're in the presentation.
Pardon?
You never left the presentation.
Okay,
It just advanced you a page and then
yeah.
another.
Let me go back here just a little bit. Yeah, there we go. This one, it should be the picture of this. Yeah, there we go. So this one is showing those vectors moving as the time goes on. Okay. So that's kind of neat. All four derivatives, including starting with the 0th, working up to the 3rd. Okay. Now, the most, I think, useful way to look at any of these harmonic oscillator, multi-dimensional harmonic oscillator pictures, any of these, this is what we're looking at right now. This one is perhaps the most telling one, right? I think this is an app called Box It that we made just to show things like this. And here we have a little molecule vibrating, so this is also used to describe vibrational motion of two masses, each in one dimension. But here is a picture of what we're doing in the sophomore Earth with 2 dimensions and 1 mass. We're making an ellipse. And this thing lets you pick any initial position and whatever velocity you want to give it, whatever that is, that will then produce an ellipse, and there's a very near ellipse like the one we first made. And the app lets you go ahead and erase the paths that you made and start over. There's the picture of the typical orbit. And the potential lines, the equipotential lines of the harmonic oscillator in 2 dimensions, and the isotropic harmonic oscillator has perfect circles for the level curves for the energy, potential energy. So this is a really nice way to describe all of that. Now I'll go ahead on the here, and this is the one that I want you to see, and I will go ahead and advance that one down there. So I have a static image down there of this particular one, and I will see if I can get the moving image of this going right here. And I think this would will do that. I hope it's set up with the right parameters. Yes, there we go. Okay, now when you look at that straight on, that is, if I set this thing up, say with an initial ellipse, it's very narrow. Suppose I make a fairly narrow ellipse here. Drag the thing down here, make it nice and large, but kind of narrow. Whatever the nervous networks are in your head immediately give you the impression of something rotating uniformly but coming out of the screen. Did everybody see that? Does anybody not see that? I think everybody is wired to see perspective. And you remember when we were talking about the perspective inside the schoolroom, right? There's scaling going on there to do that. Here the scaling is real. The thing is really going fast when it passes near to the center of force. Like right now it's really going, and then it slows down out here. Okay? That's Kepler's law, but Kepler's law is just projection of something that's uniform. Or if you stand on the beach where they have a lighthouse, and then it's just at dusk, and you can see the beam coming, right? It goes like this, it's out there taking a long time, and then all of a sudden, it goes right by you real fast, right? And then slows down. That's just projection. You look at this thing from if you can get to the top of this picture here, it's just uniform motion. So these are things to notice about just simple dynamics in 2 dimensions. This very harmonic, isotropic, perfect, very high symmetry type of motion we're talking about. Okay? So the 3 derivatives, or the 4 if you want to count the initial 0th derivative as a 4th derivative, they're all taking their turns there. Okay. Well, I would say that if we taught calculus with things like this, it wouldn't be quite as hated a subject. And that's really the objective of all of the things we do here. Try to make the presentation of difficult concepts appealing. And the computer sure help. Okay. Any questions about this? These are all, of course, things that are easy to play with when you pause it so I don't gobble CPU for other things that we might need to do today. And I will back out. And back out. Okay, let's see if there's anything else to mention. This is just a picture which something we're going to be doing later, very quickly. And that is that indeed, as your head tells you, that's some kind of rotation. And there is a way to characterize every one of the different ellipses by points on a sphere. And when you do that, there's a little thing called the spin vector that points out all of the different elliptical orbits. And it just rotates. That really does just rotate. And I'll go ahead and just run this one for the sake of it. But this is a case here, first of all, where that's changing, but I just noticed the Stokes vector is not turned on here. Let's go ahead and go to the controls just so you can see how you do that.
Last column, second from the end.
There we are, right here. Draw the Stokes vector. This is John Stokes in 1863, figuring out all of the mathematics that you use for the spinor analysis of quantum mechanical spin. And it's totally classical for the thing. So let's just reset time equals 0 here and see if I can show the Stokes vector.
Make the sign one go away.
Make the what?
Go back in your control panel.
Yeah, let's see if I'll pause, go back to control.
And then at the bottom it says base cosine function, uncheck that.
Okay.
That should have detoggled.
Yeah, write that one down.
It's already taken a picture.
Yeah, let me resume here. Where is it? Where's that T equals 0? There we go. Okay. So what this thing is doing is just tracing out with a little spin vector. This is spin precession, nuclear magnetic resonance, all that kind of stuff. We're going to talk about in Unit 4, because now it's not an isotropic oscillator anymore. It oscillates more quickly where the topography lines are close together and the gradient is high, and more slowly where the gradient is low and you have big space between the topography lines. So you get Lissajous patterns over here, which are just what that thing would like to make, except it's stuck on an ellipse. Here it's making different ellipses as time goes on. So this is what we have with the non-isotropic two-dimensional oscillator. It's a complete copy of quantum mechanics, mathematics, but done in a way that's more understandable. Okay, enough of that. We've got more fish to fry here very shortly. And that is, I want to look a bit at the Coriolis centrifugal stuff. This is compared to what we're going to do later in Chapter 12, which is coming up in the next couple of lectures. There we make Coriolis a little less confusing. But if you state it in the pictures that are going here, it is still pretty simple, and that I will put on both of these screens. Here are two situations that involve a mass in an isotropic oscillator executing a circle or a near circle. We have an orbital velocity of an earthronaut. Somebody is riding in a capsule in a evacuated tunnel. There's a perfect circle or near perfect circle around part of the Earth that's well below the surface while going here. And the idea is that riding on that, you would be weightless. Basically, the gravitational force and the centripetal, centrifugal, center fleeing force, this is the centripetal force, this is the centrifugal, that we'll be talking about in a little bit here, and that's m omega squared r. That cancels, so I'm weightless. And this case right here is doing the same thing, but the Carnival kid is saying, this is all I'm going to hold on here. I get tremendous. I feel that force. If I let go, I'm going to fly off a straight line in the direction of its current velocity. So those two things are at work here. And then when you go to an orbit that's eccentric, elliptical, you get to see these forces working all at once. And they're the thing that we'll be doing, we'll be discussing both the centrifugal and centripetal mechanics, but as well as the Coriolis, which comes next here. And I'll put it on this screen just for the sake of making it visible easily. There is some weird lighting going on there, but either one of those should work. But in any case, this is if you're on a merry-go-round and you have a velocity toward the center of the merry-go-round along that path right there. And this computer has got a weird sort of graphic anomaly, which I find going away on this newer one, so I'll use it. The idea is as you move in from that, there's going to be a Coriolis force, either the mathematician's Coriolis force, which is what the mathematician, remember, holds it back, okay? So to keep the thing there requires a force that's this way to hold it. This is where it wants to go because it had lots of velocity out here on the rim, okay? And if it was going to keep that velocity, it would be taking off in that direction. So the business force, which is the thing that tells you where M wants to go, is in the right direction. And then as you come back, they're reversed, okay? In order to get this thing up to speed, okay, and that's what this force indicates would be happening if you continue along this straight path here. And that's the force to keep it from deviating from that. It wants to deviate this way, as indicated by a little dash there. Okay, so what we need to do is when we develop our Lagrangian mechanics, it's going to make it algebraically so easy to deal with these. But when I do it this way, it takes a little bit of work, in particular when I start naming this vector a Coriolis force, and there's total inertial force. All of that needs to be fixed so that it's something that you can trust and feel good about as you work with these things. So this is all mechanics that is going to be coming fairly soon. We're going to introduce the Lagrangian Hamiltonian early in this thing. So here's a case where you're getting the same vectors as you're rising. Here you're falling. Okay, there they all are together. And I say, quite confusing. Discussion of Coriolis would be done more elegantly using